The next speaker is Olivier Jeunen, and his paper is Top K Contextual Bandits with Equity of Exposure. So, Frank?
Yes, thanks. All right, so we are dealing with a bandit setting. So this means that we have a certain agent, we have a certain user, and the goal is to show a certain list of top K recommendations to users and then see what happens. And so the goal of the agent is to learn which things it should be showing to maximize a certain notion of reward that it's going to get. We are dealing with a certain on policy setting, so this means that we have an agent that is going to show things to users and we'll show things to users and then see what happens and then learn from this. And after a certain number of rounds, there will be a model update, and then this new model will also be able to show things to users. And then after a certain amount of rounds, there will be a new model update. And so this sort of keeps on happening and happening. And the goal is going to be for the model to keep improving over time. But how does this model actually work? The most sort of typical approach is that you learn a model for a certain probability that a user will find an item relevant. And then when a user is going to come to the system, we generate a certain relevance estimate for the entire set of items. And there are several approaches to actually doing this. And so this is where the famous explore exploit basically trade-off comes in. There are some approaches based on using Thompson sampling. Some are based on things like UCB. But that doesn't really matter right now. But we get a certain relevance estimate for the entire set of items. And then we sort them basically according to having the most relevant items on top and the least relevant items sort of down there. And so the main question that we ask in this work is whether this is actually really what we want to do. And the reason that I'm asking that is because a click is not just about relevance, it's also about being sure that the item is actually being exposed to the user. So we say that a click is just it's a random variable that can be factorized into two things. On one hand, you have relevance, but on the other hand, you have exposure. And so why is this a problem? Well, we can basically see an example where we are a music streaming service and we have a perfect model, for example. So we know the true probability of relevance for the entire set of items. Then we can basically show this list to a user, and we have a certain user model that is going to tell us that this is the probability of exposure at each list in the set. Now, the main problem that you see here is that even though there's only a very small difference in the relevance between the first item and the item at the last position, there's a huge difference in exposure, and there's a huge difference in the expected clicks. And this is really going to be an issue because when you're a music streaming service, clicks lead to streams, and streams lead to basically sales for these people. And so the difference in the relevance is going to be very, very small, but there will be a huge difference in the sort of impact for these artists. And so in music streaming, for example, or in job recommendation, these are things that are very important, and we should be very aware of them. We are certainly not the first people to actually think about this. And there was a great paper at CIKM last year which proposed the principle of equity of exposure. And so they say that given a fixed information need, there is no item that should actually be getting more or less exposure than the other items of the same relevance. But so the main problem here is that they assume that you have a binary label, being some items are relevant and some are not. But that's not the case with us, because it's just a random variable, and there's some certain probability that a certain item is going to be found relevant. So we sort of tweak their goal a little bit to say that we want our clicks on the top K to be sort of distributed in the same way as relevance. So we are going to try to minimize the divergence between these two conditional probability distributions. But so because we said that clicks are actually just factorized into relevance and exposure, if you want clicks to be dependent on relevance alone, this means that we should be randomizing exposure. And randomizing exposure is a fancy way of saying we need to shuffle the top K. And so that all sounds very, very nice, but if we shuffle the entire top K for a large K, this might be a very bad idea, because then we might just be getting no clicks at all anymore. So instead, we propose to basically try to maximize the expected number of clicks whilst minimizing this divergence. And that is the only thing that is going to change. So we actually still have the exact same model in production, but the only thing that is going to change is how we are actually going to sort these items. And so that is really going to be a really simple approach to actually get working in production, I must say. And so we call this exposure-aware arm selection. And so let's look at an example where we might have a certain user where we show how much they basically like the items in the catalog on the sort of x-axis. And so we might have a very focused user who likes a few items really, really well, but then it basically dies down pretty quickly. We might have some other users for which this happens much less quickly, and we might have some users who are actually very diverse, and the top 10, for example, is actually very, very similar in terms of relevance for this user. So we might actually shuffle the entire top 10 for this very diverse user and not lose that many clicks, but for the very focused user, that is going to be a bad idea. So we do a personalization of this, the size of the the size of the head that we are going to reshuffle actually in practice. So it's a very, very simple approach, I would say. But does this actually work in practice? We use data from a paper by Bandana et al. From last year here, actually. And these are music recommendations on a streaming app. And we use a state-of-the-art bandit algorithm with our model basically on top. It's called Bayesian logistic regression with Bayesian logistic regression with Thompson sampling. And then we compare several sort of arm selection strategies. So the first one is really just to sort of greedily rank the items. We can do ears with a fixed K, and we can do ears with a sort of personalized K, whilst varying the sort of tolerance of the clicks that we are willing to lose for improved fairness. And so we see the results here. So the plot on the left is showing the expected number of clicks. So the blue line is the greedy approach, which is, of course, going to be doing really, really well. But for very small values of epsilon, we can see that we're actually really, really close around that neighborhood. But as we improve epsilon, we are losing more and more clicks. The middle plot is then showing the fairness. So we can see that the greedy approach is actually the least fair of them all. But with small increases to the tolerance parameter, we see that there is a large decrease in fairness already. And then the plot on the right is actually showing a trade-off between clicks and between fairness. And so we see that the red dots there, they are not on the Pareto frontier. And so this basically means that when you don't personalize how you are going to do this exposure-aware arm selection, there is a very simple way to actually get closer, get more fairness for the same amount of clicks, or more clicks for the same amount of fairness, actually. Yeah, and that's it. So I would say that these methods are actually a very, very good amount, a very, very good approach to basically doing recommendation, but just greedily ranking the items might just not always be what you want to do. And so instead we propose ears, which is basically, it's basically model agnostic, so it's very, very easy to actually do in production, I would say. It's a principled way to actually make sure that clicks have a similar probability distribution as relevance, and it's going to tackle the relevance fairness trade-off in a personalized manner. That's it. There is a QR code for the slides, the paper, and for the code there, and I'd be happy to take any questions. Thanks.
Thank you. So we do have one question from the online audience.
Okay.
The question is, your setup is assuming that you don't know what was exposed, or let's say the impressions to the users. So the question is, in case you know what was exposed to the user, can you model directly the probability of exposure?
Yes, so we do that. So we do assume that you have a certain user model, and that is what you use to actually get a certain estimate for the probability of exposure for a certain item. And so that is what you're going to use when you are going to compute the expected number of clicks with a certain tolerance. And so that's really crucial to actually go from this parameter epsilon to the size k that you're willing to reshuffle, actually. So we do assume that you have that.
Okay, thanks. And if there are no, well, plenty of questions now, okay? So I have to pick some of them because we don't have the time to go through all of them. So
all right.
Do you need to know exposure probability at each ranking position or not?
Yes, you do. But you're not limited to a certain user model, I would say. So for the experiments, we make use of a cascading user model. So the probability of exposure for a certain item in the list is also going to be dependent on the previous items in the list. And so there are many ways to actually do that, I would say, but you would need to have a model that makes sense. Because if it's a bad user model, then I'm assuming it's also going to be a wrong estimate of the expected amount of clicks that you would get, and then you're off. But yeah.
Okay, thanks. There are so many questions, and
okay.
I will use
it's very nice to hear.
There is also a question here from the audience. Okay, perfect.
Yeah, hi.
Yeah, thanks for the nice talk. So I was wondering, how does your work fit the broader landscape of work on fairness? So how do you position your work in relation to other metrics that have been there?
Yes. There is way more in the paper about that. But I would say that there are many works that are really focused on learning rankings and really sort of learning a fair ranking. Whereas here we are basically more focused on you have a certain model and then you need to choose how you actually do this like re-ranking, basically. And the second part is that we're basically really focused on the bandit setting, where because we are able to lean on these existing algorithms that are basically provably optimal for these on-policy bandit settings, it's actually really nice that we don't need to change them there. And so that's one thing that I don't think many other methods have. But there's much more in the paper about that, about all of the other work that basically has been done in this area. Thank you.
And well, there are so many questions, but I will take advantage of being the session chair to do my own question.
Okay.
and maybe my question is naive, but is it possible to simply modify the rewarding function in order to take into account the exposure, or maybe I'm missing something?
I would assume so, yes. So there are many methods that actually do that. But here we really just learn a model for the probability of relevance, and we assume that that's something that you can get from the clicks and the exposure. I'm assuming you can have different rewards as well, but some things would need to be changed in the background then. Because now it's really just about learning the probability of a certain event happening, let's say. I mean, there certainly would be a way to do it, but I don't see it right now in my head very clearly how to move forward with that. Yeah.
Okay, thank you.
Okay.
Thank you again,
Thanks.
Olivier, for your presentation.
Yep.
And so we can, thanks again, Olivier.